let's go into today's topic. Now, I need you to pay attention. You know why? Because what we want to discuss today is one of the cornerstone of statistics that we call normal distribution. I want to welcome you to normal distribution. Okay, in the outline. Of course, I'm going to walk you through uh, the focus today will be on univariate. When I'm focusing on one measurement at a time and the distribution is normal, I'm actually going to walk you through how do we the history. I'm going to walk you through the history of normal distribution and why is it that normal distribution is applicable everywhere in statistics and not only in statistics, across a variety of fields. I'm going to discuss all of that today. I'm also going to discuss what I call the parameter estimation in normal distribution. Of course, on Wednesday, the focus will be on bivariate, and on Friday, the focus will be on multivariate or normal and sampling distributions. I want us to, I want to get started. Let me start with the history. Are you ready? You want to hear the history? Okay, let's get started here. It started with the movers, the movers in 1733. Now let me tell you this. The movers actually migrated from France. He left France at the age of 20 and he left for England. Has anybody heard about England? England in the United Kingdom. And upon arrival in England, he actually associated with Sir Isaac Newton. Has anybody heard about Isaac Newton in physics? Maybe you've heard about universal gravitational law, stuff like that. And he also mingled with some mathematicians. And you know what? The movers Abraham Dimbovas actually liked playing games and he was trying to figure out the probability of winning a game. Of course, we all know when you go on a game, it's either you win or you lose. And he said, when I'm having two events here, and in statistical theory, okay, when when there are two possible outcome, okay, we normally use binomial distribution. Has anybody heard about binomial distribution? Of course, in 5101, binomial distribution actually we're told that it model outcome event with two possible outcome, and don't forget the movers was actually playing a game and he was looking for a way to predict the probability of winning. But let me tell you this, using binomial, when the sample size is large, okay, when the sample size is large, the binomial will be difficult to use. Okay, so Laplace find it difficult to use binomial distribution to estimate the probability of winning a game when the sample size is large. Okay, and he now try to use the idea of a normal curve. He was the first person to use a normal curve. Okay, normal distribution is a probability distribution of a continuous random variable, while binomial distribution is a probability distribution of a discrete random variable. But you know what Abraham de Moivre did? He actually approximates binomial distribution with a normal distribution because the binomial distribution will be complicated, when the sample size is large. You can't use it, but as at that time, they don't. I do not think they have a computer that can really handle that. So he now used what I call the normal approximation, and he had a breakthrough. Even he gave a condition. Of course, you did that in 5101 when the sample size is large, okay, and the NP, the product of the numbers of trial and the probability of success in binomial converges to mu in normal. Okay, he was able to have a breakthrough. Now that was in 1733. Okay, but in 1788, there was another philosopher, mathematician, called Laplace. Okay, I said De Moivre in 1733, Laplace in 1788. Now, let me tell you this. Laplace used normal distribution. He was trying to work with um, a particular data set that do not come from normal distribution, but he realized that the sample means when n is sufficiently large, okay, the sample statistic or the distribution of sample statistic become normal. So Laplace introduced the concept of central limit theorem. You've heard about central limit theorem in statistics 5101. You know, even though you are choosing a data set from non-normal population, but the sampling distribution of statistic. When I say sampling distribution of statistic, I mean sampling distribution of mean, sampling distribution of proportion, and so on like that. The distribution of that become normal. Okay, so Laplace was able to show the world that if you are not sampling from normal population, that's okay, but provided your sample size is sufficiently large, then the sampling distribution of your statistic become normal. Okay, and that is why every other feed started using normal distribution. Okay, they started using normal model. Okay, even though they are not sampling from normal population, but they are guaranteed the moment they choose a sufficiently large sample size, of course, the sample statistic will follow normal. But you know what? De Moivre Laplace did not derive the density function of a normal distribution. They were using normal curve. But in 1809, okay, okay, Gauss derived the density function that you are seeing right now. Take a look at this guy. Equation one, it was Gauss. And that was why they renamed normal distribution a Gaussian distribution, because Gauss actually provided us the mathematical framework of the distribution, and Gauss also enabled us to see the parameters in the normal distribution. The parameter is the mu and the sigma. The mu is the mean, which is the center. Okay, why the sigma is the standard deviation. I remember Gauss actually applied this to measurement error. Okay, he believed that the measurement errors, of course, we can't do without errors in measurement. Okay, the measurement errors follow normal distribution. Okay, this was actually discovered by Gauss, and the belief is this: you know, small deviations of the errors are common, why the large deviations, from the mean, they should be very rare. Okay, in that situation, is actually going to say, oh, that is symmetrical. Symmetrical in the sense that, okay, at the center, I'm going to have a lot at the center, but at the tail, I'm going to have few at the tail. Okay, which means the deviation from the mean, small deviations from the mean are expected to be large, while the large deviation from the mean are expected to be small. So I present to you a normal distribution. Okay, now I'm actually going to tell you the significance of normal distribution moving forward. Okay, I think I just handled the historical, background, you know, coming from the three fronts. I think I gave you the De Moivre's, the Laplace and the Gauss. But you know what? Let's talk about significance of this distribution. Okay, the number one is its model natural phenomenon. When you look at the behavior of natural phenomena, like I could have some variable like height, weight, they are approximately normally distributed. Some biological traits, some social traits, okay, follow normal distribution. Now, the reason why is it that this particular distribution dominates everywhere? It dominates everywhere because of central limit theorem. Because Laplace in 1788 was able to show the world, you shouldn't be worried if you are not sampling from a normal population, but provided you are choosing a very high, if you are choosing a very large sample, your sampling distribution of your statistic will be approximately normal. Okay, so the reason why it is interesting, the reason why it dominates application in every field is because of central limit theorem. Now, another significance of normal distribution is what I'm going to call it is a foundation of statistical inference. Why do I say foundation of statistical inference? Without normal assumptions of normal distribution, you cannot conduct a t-test. One sample t-test, two sample t-test, analysis of variance test. You can't achieve that. You cannot, conduct that without all of that rely under the assumptions of normal distribution. Does that make sense? So without normal distribution, you are never going to have, then figure out. Now, I'm also going to talk about another significance is mathematical convenience and structure. Let me tell you this. As time goes on, and I know in 5101, do you know that if I'm talking about this a marginal distribution, if I'm focusing on distribution of one variable at a time, I'm talking about marginal. Do you know that if I'm also talking about conditional, it's also going to be it can be normal too. Okay. We know when you have a marginal, it's going to be normal. We can preserve normality when you are also working with the conditional distribution. In on Wednesday, or under bivariate distribution, we're going to be talking about conditional distribution. So, maybe I got two variables, and these two variables, maybe the first one is a proportion of time. A driving facility is used in a bank, and another variable, the proportion of time a walk-in facility is used in a bank. Don't forget, in a bank, they have a driving facility, they have a walk-in. Okay, now if I want to figure out the probability of those who will walk in, given that I know those who drive in, that's a conditional function that I need. Okay, we can also have a normal distribution in that regard. So, and that's why I say mathematical convenience. Let me also say this. We derive some other important distribution from normal. Okay, we derive other important distribution for normal. Okay, for instance, if I t what you have done in this in 5101, if I have this guy, okay, this is the origin of a t distribution. Okay, now take a look at this. The z is a standard normal distribution. The v is the chi-squared. And you know what? Chi-squared distribution is derived from normal as well. So the t-test, which means, and that's why as one of the assumptions of a t-test is normal. It has to be normal, assumption of normality, because deriving t-test, t-distribution is actually as an origin in a normal distribution. Okay, not only that, what about your F distribution that we use in analysis of variance tests, where you want to compare more than two means? You make use of F test. Without F distribution, you can't conduct an F test. And you know what? If you look at the ratio, it is U over R1 divided by V over R2. Okay, F distribution is derived from the ratio of two independent chi-squared, and each of the independent the chi-squared has their origin in normal distribution. And that is the reason why one of the assumptions of analysis of variance test is that it should follow normal distribution. Okay, now there's a lot, this provide a benchmark to every other distribution. How do I know there's an outlier in a data set? How do I know there's a skewness? How do I know there's a kurtosis? We measure all of that relative to normal distribution. And let me also tell you another important, significance of a normal distribution is because it can facilitate standardization. For instance, if I want to compare variables, different variables that have different scales, comparability. Okay, I can actually standardize the variables to actually restrict them to have a mean of 0 and a variance of 1. Now, because normality facilitates standardization, standardization facilitates easy probabilistic computation. Because with standardization, you can make use of your statistical table. Has anybody make use of statistical table before, where you check a z-score value and stuff like that? So it is standardization that make that easy. Now, this is the curve, and when I standardize normal distribution, like I said, I'm restricting that to have a mean of 0 and variance of 1. Okay, which means I can compare data set across different variables with different scales. Okay, now when I can standardize it, I'll be able to compare that. Now, how do I find the probability? Let me tell you this. Initially, when when you don't standardize, if you want to find probability with this density, that will require rigorous calculus knowledge. But you know what? Because we can standardize, okay, it's going to be easy. Standardization will facilitate the use of a z-table. Instead of us to go through into rigorous calculus, we're not going to do that. Standardization will make things easy. Now that's what I'm doing here. From the calculus perspective, the probability of S lie between A and B, maybe S is weight. I want to figure out what is the percentage of my patient we have between maybe a particular values of weight. Okay, now I'm actually going to do that in calculus time, but that's no problem. I can make use of a z table. Now, how do I know my data set follow normal distribution? Of course, we have several ways to investigate that. You can make use of histogram. You can make use of probability plots. You can make use of box plot to figure out whether it follows normal distribution. We also have different kind of tests that we can conduct. Tests of normality, like Shapiro-Wilkie test of normality, Adamsi-Darling test of normality, Kolmogorov-Smirnov test of normality. So there's so many ways we can test whether the distribution of our data follow normal. But you know what? We also have an empirical way of showing that if data set follow normal distribution, it is believed that 68% of the data set should fall within one standard deviation, while 95% should fall within two standard deviation, and 99.75% should fall within three standard deviation. Okay, you've done all of this in 5101. Now take a look at this. Do you know with standardization, I can compare averages of from more than three groups? Take a look at what I'm doing here. If you take a look at this guy now, okay, this is comparing averages. If you take a look at what I have, okay, uh, they have different Sarah, they have different standard deviation. Okay, so this is actually comparing different values of parameter of a normal distribution. Okay, so this is the PDF and this is the CDF. Now let me also say this. When S follow normal distribution, if there is this Y, that's a function of S, linear combination will also follow normal distribution. So linear combination is closed under normal distribution. Okay, so if Y depend on S and S follow normal distribution, Y is also going to follow normal distribution. So the mean of Y is going to be this guy, the variance is going to be that. So this is an example. Okay, this is an example now. Suppose that X follow normal with a mean of 1, the variance of 2. Determine the distribution of this. You've done something like this in 5101. Okay, now this is the calculation. Now you can actually revise what you've done before. Okay, so if X follow normal distribution with a mean of 1 and the variance of 2, I can determine the mean and variance of a linear combination. That's what you're seeing here. Okay, so that's exactly what you're seeing here. Okay, so you know what I'm actually using. Okay, you take a look at this guy. I'm using this guy, right? Okay, to be able to figure out what the mean is. Okay, so if I have X plus 3, and the mean of S is 1. Automatically, the mean of Y is adding that 3 to 1. That's going to be 4. And that's why you have this mean here to be 4. Okay. If I have 2S plus 3, okay, and the mean is 1, what is 2 times 1? 2. 2 plus 3, that's 5. That's why you have this mean here. If I have 3x plus 2, and the mean, you've been told that the mean is 1. If you plug in 3 times 1, 2, sorry, 3 times 1, 3 plus 2, that will be 5. Okay. Now, how do you get the variances? Of course, you actually got to make use of this. This is the explanation for the variances. Now, you know where I'm going to start tomorrow? Sorry, or Wednesday. I'm actually going to, like, you have not seen this before in your 5101. This is the one you've seen all the way to this page. You've seen that in 5101, but there's a new information. What you've not seen before now is, how do I estimate my mean and variance, which are the parameter of a normal distribution from my data set? If I'm working with my data set, okay, and I'm assuming normal, how do I estimate the mean? How do I estimate the variance? Because in 5101, they've been giving you the mean and variance. How do you now get it from data? That's where I'm going to start next, using the method of maximum likelihood estimation. Okay, so this is where I'm actually going to stop today. On Wednesday, I'm actually going to continue from here. Okay, is there any question for me? Make sure you all stay safe and have a lovely day. Bye for now, everyone.